This is the second video in the lessons for section 13.1. So far we've gone over the trig identities and some of the definitions for trig functions and the methods of proof. Now we're going to implement those methods and try to work through some of these examples. So if you look at this first example here, we have cosecant of theta times tangent of theta, and we want to prove that that equals secant of theta. And there are several ways we can go about doing this. First method, if we want to go with our methods listed above, method 1 talks about using those trig definitions. So we can convert cosecant of theta, again this is the reciprocal of sine, so this would be 1 over y, and tangent we know is y over x. And so then we can do some algebra. Again, this is what we're doing here. We're converting these trig things into things that we can think of as algebraic. Y divided by y is 1. And so we are left with 1 over x. And we know by definition 1 over x would be 1 over cosine. And 1 over cosine is secant. So in this case we're not necessarily trying to manipulate both sides. We can do that if we want to, but it's a little bit easier if we just kind of stick with the more complicated side and try to get to the simpler side. And in this case we did. We got to secant of theta and everything worked out okay. We could have tried a different method. We could have looked at using those trig identities that we have. Again, cosecant of theta is 1 over sine of theta, and tangent we know is sine of theta over cosine of theta. So you can see how this is kind of working out similarly as we had above. Sine theta divided by sine theta is 1. Again, this only works because they have the same angle theta and there's no powers like squared on anything. So this ends up being 1 over cosine of theta, which again we know is secant of theta. So again, all we're doing here is we're trying to get to typically the right hand side of the equation and checking. So this is kind of like when you're checking work in algebra. So let's try to look at another example here. 1 over cosine squared. We talked about this up above in the previous section. Again, we said 1 minus cosine squared was sine squared. If you need to, you can go back and rewatch the last video, but this comes out to be sine squared of theta. So we can replace that with sine squared, and then we have cosecant squared of theta. Well, cosecant is 1 over sine, so we have sine squared of theta times 1 over sine, and this is squared, so it would be 1 over sine squared of theta. Again, sine squared of theta divided by sine squared of theta is 1, so we end up with 1, which is what we wanted. So I want you to pause the video here and try example 3. So again, you could have used either of the methods we talked about before. It's a little bit easier maybe to kind of stick with the trig functions, at least I think so in this case. 1 plus tangent squared, again going back to those Pythagorean identities, we know this is secant squared of theta over tangent squared of theta. Secant we know is 1 over cosine, so we get 1 over cosine squared. Tangent is sine over cosine, again those both get squared. We use multiplication of the reciprocal to do division of fractions, and we end up with 1 over sine squared, which is cosecant squared. If you instead want to go with the x's and y's, you have 1, tangent is y over x, again those get squared in both cases. Multiply by the least common denominator, which is x squared. That gives you x squared plus y squared on top and y squared on the bottom. We talked about before when we're dealing with the unit circle, which we are in this case, x squared plus y squared equals 1, our radius squared, and still over y squared, but y is really sine, so we get 1 over sine squared of theta, which again is cosecant squared of theta. So again, that's just two different ways. You don't have to do it both ways. I'm just showing two different ways to let you know that there are multiple ways to look at these problems, and you can work through whichever you feel most comfortable. Sometimes it's easier to use one method over another. Sometimes it's just picking a method that you feel comfortable with and kind of going with it. So let's take a look at another example. We have cosine squared minus 1. In that case, again, if you kind of go back to the Pythagorean identities, we didn't quite work this one out, but again, you can come up with this. Sine squared theta plus cosine squared theta equals 1. So this is kind of what we would call an aside. This isn't actually part of the problem yet. We're just trying to get to this cosine squared piece. If we move the 1 over and move the sine over, again, we're going to subtract these so that we can kind of move things around the way we want them to. We'll end up with cosine squared minus 1, and on the other side we'll end up with a negative sine squared theta. So it's possible we want to do that at sometimes too. Again, you're kind of looking at what is going to match up best with what you're given. We can go with the x's and y's, and I'll kind of show you that in a second as well. So this was our little aside here. Let's go to the actual problem. Cosine squared theta minus 1 is negative sine squared theta, and this is over sine of theta. Now, just like any time you would have x squared over x, we can simplify this as well. This will get rid of one of the signs in the numerator, and we'll be left with negative sine of theta, which is what we wanted. If we wanted to go through and do this with the x's and y's, then cosine is x squared minus 1 over sine is y. Again, it's a little bit harder to kind of see what's going on here. And you can kind of see how it's not really going to get you anywhere with this one. It's going to be really hard to kind of move along. You can, again, go back to this aside that we had up here. That's really the only thing you can do. So I'm going to move this over. Kind of do another aside. Again, x squared plus y squared equals 1. So again, if you kind of move things around, x squared minus 1 equals negative y squared. Again, kind of moving things around just like we did up here. And you end up with negative y squared over y, which again simplifies to be just negative y, and we know that sine is equal to y, so negative sine of theta. A little bit trickier to see, I think, in this case, but whichever one you prefer will work out for you. We'll look at a few more examples here. Tangent of x, again, we can use x instead of theta, that's perfectly fine. Just pay attention to which variable is being used in each case. Tangent of x plus cotangent of x is equal to secant of x cosecant of x. So again, if we rewrite our tangent as sine of x over cosine of x, and we rewrite our cotangent as cosine of x over sine of x, and then we find a common denominator, which in this case is sine times cosine, so we would multiply the first fraction times sine of x over sine of x, and we would multiply the second fraction by the cosine of x over the cosine of x, and we would end up with a sine squared of x and a cosine squared of x over our common denominator, just sine x, cosine x. And again, I don't want to see anybody trying to cancel anything here. That's bad algebra. And we've got a plus sign here. We can't split these up. They're stuck together. These are multiplicative factors, and yes, they can be simplified if there happened to be a factor up top to simplify them with, but there's not. This is a term, this is a term. Terms cannot, quote, cancel, even though I don't like that word. Only factors can simplify or, quote, cancel. What we can do, however, is we know that sine squared plus cosine squared is equal to 1. And we can split this back up into separate fractions. 1 over sine of x times 1 over cosine of x, and the only reason we can do this is because it's multiplication. If this had been addition here, we could not do it. And we know that 1 over sine is cosecant of x, and 1 over cosine is secant of x, and that's essentially the same thing that we have here, just rearranged. Again, multiplication is commutative, meaning that we can switch the order and still get the same result. Again, I want you to pause the video here and try example 6. So for this one, just like the others, you can go about it different ways. I have two listed here. One is to break down that 1 plus tangent squared is secant squared, replace that with 1 over cosine squared, replace tangent with sine over cosine, again squared, multiply by the reciprocal because we have fractions. You end up with 1 over sine squared, getting you to cosecant squared. Or this one's actually a little bit simpler, and it only works because we have a single term in the denominator. If there had been addition or subtraction in the denominator, we can't use this, but it works out nicely here. We have 1 over tangent squared x plus tangent squared over tangent squared x. 1 over tangent squared is cotangent squared. Tangent squared over tangent squared is 1. And again, by the Pythagorean identities, we get to cosecant squared of x. So both of those work. Again, you can go with the x and y method, and that works equally as well. Again, you're kind of plugging in your y over x for both of those tangent terms, multiplying by your common denominator x squared like we did in the earlier example, knowing that x squared plus y squared is 1, and then that leads you to cosecant squared of x. Got some more examples here. These ones are actually kind of look at factoring and how that can affect, at least this next one is. We've got tangent squared minus tangent squared sine squared. So first thing it might be helpful to do is to factor that out since it's in both of those. So you get tangent squared of x, you factor that out, you're left with a 1 in the first place and a minus sine squared x in the second place. We know that 1 minus sine squared, again going back to the Pythagorean identities, we know that that is cosine squared. And we know that tangent is sine squared over cosine squared. So cosine squared divided by cosine squared is 1, and we are simply left with the sine squared x that we were looking for. In this next example, we actually want to distribute instead of factor. So we look at distributing, we've got cosine of theta, cosecant of theta, minus cosine of theta times secant of theta. Again, we can either convert to our x and y components here, which I'll do kind of down. Cosine is x, cosecant is 1 over y, minus cosine is x, secant is 1 over x. So we end up with x over y minus x divided by x is 1, and x over y we know is cotangent of x, or cotangent of theta, and 1 is just 1, so that gets us to where we needed to go. If instead we wanted to stick with the trig functions instead of the x and y, we have cosine of theta times 1 over the sine of theta minus cosine of theta times 1 over cosine of theta, and you can kind of see how this is going in the same direction. You end up with cosine of theta over sine of theta minus cosine of theta over cosine of theta, which is 1. So you end up with cotangent of theta, cosine over sine, minus 1, which again is what you wanted to get to. So just two different ways, again, of going about this. If you want to use one over the other, that's fine. Just make sure you're comfortable and that you can use whichever one's more effective when necessary. Okay, we're going to take a look at one more example, and then I'm going to have you guys work through one. This one we can think of as the difference of perfect squares. Technically, to the 4th power is still a square. We've got a difference here, subtraction. So I'm going to factor this into cosine squared of x minus sine squared of x, and cosine squared of x plus sine squared of x. Again, cosine squared of x plus sine squared of x is just 1, and we're trying to get to sine, and this is the other thing you have to pay attention to sometimes of why you want to substitute certain things in. If we're trying to get things in terms of sine, we want to simplify, for instance, cosine squared of x, we know from the Pythagorean theorem is really 1 minus the sine squared of x, and then we still have a minus sine squared of x. Again, we said cosine squared of x plus sine squared of x is just 1. And now we have 1. If we simplify, we end up with 1, and we've got 2 of these sine squared, so it would be minus 2 times the sine squared of x, which is what we wanted. Again, if you prefer to use x's and y's, we can kind of start off at the beginning. We would have x to the 4th minus y to the 4th. Again, we would factor x squared minus y squared, x squared plus y squared. Again, x squared plus y squared we know is 1, and using again the same Pythagorean identity, we're trying to get this to be 1 minus 2y squared. If we're again, sine is y, so we're going to try to get x in terms of y. We know that it's 1 minus y squared, and then minus another y squared that we had from before. And x squared plus y squared is 1, so we end up with 1 minus 2y squared, which is what we wanted to get to. So I want you to look those over again, make sure, sometimes it helps to see the x and y just to kind of see what's going on with the sine and cosine. Really, we're just kind of treating those as variables, treating those as whole terms and not necessarily as the trig pieces themselves, but when you convert them to x and y, you can see a little bit more of what they are as the trig pieces. So I want you to pause the video here and try example 10. Again, notice you're probably going to want to try to factor. So if you look here at example 10, and again you can probably do this in fewer steps than I have listed here, but I was just kind of trying to show all the steps here. We factored the tangent out, replaced cotangent with cosine over sine, simplified that into one fraction in the next step, then simplified this whole inside into one fraction by finding a common denominator. That's what we get here, remembering that sine squared plus cosine squared is 1, and that tangent is sine over cosine. Doing some simplification, we end up with 1 over cosine of theta, which is secant of theta. So this whole big mess here can be simplified down into secant of theta, which is why we choose to do this sometimes, because we want to end up with something simpler. Mathematicians like things simple, believe it or not. Let's take a look at another example. We've got sine times cotangent. We can go simply with the trig identities. Sine of x, cotangent is really cosine of x over sine of x. Simplifying sine over sine to get 1. Again, this is not 0, this is 1. We end up with cosine of x, which is relatively simple. If you instead wanted to go with the x's and y's, sine is y, cotangent is x over y. Again, y divided by y is going to give you 1, and you are left with x, which we know is cosine. Again, don't confuse this x with this x, they are technically different. In this next one, we actually want to go through and combine the denominator, multiply them through. Sometimes we factor, sometimes we multiply out. So if we do that, we have sine of theta times the cosine of theta. If we go through and multiply this out, again, this is difference of perfect squares, we end up with 1 minus the cosine squared of theta, which we know is a Pythagorean identity. So this gets us to sine of theta cosine of theta over sine squared of theta, again with that Pythagorean identity. This sine is going to divide with one of those sines, leaving you a 1 there. So you're left with a cosine of theta over a sine of theta, which again is cotangent of theta. And again, you could go through and work this with the x's and y's if you prefer. Let's look at one more example here. Again, I want you to pause the video and try this last example, and then resume the video to check your work. So again, for this one, if you just went with the trig identities and some simplification, we can do common denominator between these two fractions. We would end up with negative 2 over sine squared theta minus 1 when you multiply those two denominators together. Which, if you substitute sine squared minus 1 for negative cosine squared theta with the Pythagorean identity, negative and negative are going to give you positive, and you're left with 2. 1 over cosine is secant. We're going to look at a few more examples here, and these are trying to get us to simplify things in terms of sine and cosine. We're not setting them equal, trying to prove something in this case. We're actually just trying to simplify. As you see here, we've got cotangent and cosecant, which we could automatically convert to sine and cosine, but that might not necessarily be our best bet right off the bat because we've got this 2 here. Instead, whenever we see a number plus one of the trig functions squared, it's usually good to go back and look at those Pythagorean theorems and see if they will help. And just a note here, it's possible that you'll try something and it won't work the first time, and that's perfectly fine. Go back and try a different method. We've learned several methods and there are several identities to go through. You'll pick this up and be able to move through things faster and recognize things the more you practice. But at the beginning it's possible you'll try something that doesn't work and then you need to go back and try something different, and that's perfectly fine. Don't get too frustrated. It's possible that you need to try more than one method until you get it right. So we've got 2, if you remember from the Pythagorean identities, cotangent squared is equal to cosecant squared theta minus 1. And this is over cosecant squared of theta. You might be tempted to kind of simplify there. Don't. Again, you've got plus and minus here, so that's not going to work. We also have our minus 1 that was up here. On the numerator here we have 2 minus 1, so that's going to simplify to be 1 plus cosecant squared of theta over cosecant squared of theta. And again, this is the step where I'm talking about it's possible that you might not necessarily pick the easiest path right off the bat. You might have to try multiple things because it might be tempting. This 1 plus cosecant squared looks like something from the Pythagorean identities, but if you go back to those, you're actually just going to get back to where you started. So instead, what I'm going to do here is I see that we've got a single term in the denominator, so I'm going to split this up into 2 fractions. And that's going to be 1 over cosecant squared of theta plus cosecant squared of theta over cosecant squared of theta. Then we still have our minus 1 there. And this is nice because it simplifies 1 over cosecant squared. We know cosecant is the reciprocal of sine, so we end up with sine squared of theta. Cosecant squared over cosecant squared just ends up being 1, and then we have this minus 1, and those would end up subtracting to be 0. So all we are left with here is sine squared of theta. So we've simplified this in terms of sine and cosine. We didn't actually have a cosine in this case, but we simplified without having to convert those original things there. So I want you to pause the video here and try example 15. So for this one, again, when you convert everything over to sine and cosine, again, sine is going to stay as is, secant will change to 1 over cosine, and again, that's squared. Tangent will convert to being sine over cosine, and cosecant will convert to being 1 over sine. And then you can simplify that denominator. Those signs in the denominator would divide to be 1. So in the numerator here, we've got sine over cosine squared, so that's written in our first fraction here, and then sines simplified to be 1, so we're just left with 1 over cosine here, but since we're dividing that whole thing, we flip it over, so it would be cosine over 1, or just cosine. And now again, one of these cosines, this cosine here simplifies with one of the cosines in the cosine squared, and we're simply left with sine over cosine. Now typically we would convert this back over to being tangent, because tangent is sine over cosine, but in this case it asked us to leave things in terms of sine and cosine, so we're going to do just that. We have one last example here, and that is to factor the trigonometric expression that is given. Again, like I said, sometimes we need to factor things. First thing you always want to look for, just like when we're dealing with regular algebra, is to find a common factor. In this case, all of these have a sine, so we're going to factor out that common sine theta, and we're left with a tangent squared of theta minus 3 times the tangent of theta and minus 10 when we factor out that sine theta. Now this might look a little confusing, but what we could do is instead, let's say that a is equal to tangent of theta. When we do that, we can rewrite this as a squared minus 3a minus 10, and we know how to factor that from algebra. I said before we're going to be doing a bit of algebra here with our trig. So we end up, when we factor that, we get an a minus 5 and an a plus 2. Again, you can kind of verify that. And then finally, we just substitute that back in. So instead of a, we have tangent. So we have tangent of theta minus 5 and tangent of theta plus 2. And so this is the complete factored form. This is going to come in handy when we get to solving equations with trigonometric functions involved. And this will conclude the videos for section 13.1.